This is lecture 2 from chapter 13, and we're picking back up talking about different types of radiation from the radioactive elements from their breakdown. So we've talked about alpha particles and beta particles. You might also see them listed as alpha rays and beta rays. So we saw that alpha rays or alpha particles, those are actually like basically helium nuclei without the electrons. And then beta particles or beta rays, those are electrons from the breakdown of the neutrons. And then the last we get are gamma rays. So gamma rays, these are a little different. Like I said, they are actually not particles that are emitted during the decay of the nucleus. These are high frequency electromagnetic irradiation. So when we saw the electromagnetic spectrum before, we saw there were light rays, there were X-rays, and then gamma rays. So if you remember the electromagnetic spectrum, we saw it going this direction. Light rays were right in the middle. These guys are to the right hand side. So they are very high frequency, pure energy, so not a particle. And because they have no mass and no electric charge, they can penetrate all but the most dense materials. So that's the thing that slows down alpha particles, is their size, their mass, and what slows down beta particles because they're electrically charged with that negative charge. But because gamma rays are just pure energy, there's nothing to slow them down. So in order to stop gamma rays, you need something like lead. This is why when you go to get an X-ray at like the dentist, they're going to give you a lead apron because X-rays are a little lower frequency. And they'll be stopped by lead. Gamma rays, same thing. They'll be able to be stopped by a section of lead. The thing is that of the different types of radiation that we talked about so far, gamma rays are the most dangerous because they are pure energy, and they are such high frequency energy that they're very damaging. And they take so much protection in order to protect you from this energy. The only exception is if you swallow the other two. So I know that sounds funny, but if you swallow alpha or beta radiation, they're going to do quite a bit of damage because they bypass any of those protective layers like clothing or aluminum shielding or anything like that. And so, sorry. They are going to be able to bypass that and do direct damage. And since they are big and or charged, they can do quite a bit of damage if they can get direct access to your tissues. So just a little bit reminder here, this is just showing you the different rays and what can stop them. So here they're shown with their Greek letters. So alpha radiation can be stopped with paper because of their mass. Beta radiation can be stopped with something like aluminum because of its charge. But gamma radiation can make it through all of that. You're going to need something very, very dense like lead in order to stop gamma radiation from a radioactive source. So radiation in our everyday environment. So where are we getting this? Like I mentioned, a majority of our radiation is coming from outside sources like cosmic rays. But we get exposure to a lot of it from rocks and minerals around us. They can contain high amounts of radioactive materials, especially actually here in Ohio. And what we found is that brick, stone, and concrete homes are going to have higher levels of radioactivity than wooden ones because of this. Living organisms do absorb radiation, however, they have a very low amount of it, so that's why wood is going to have a low amount of radiation compared to these brick, stone, and concrete structures because they're going to contain these rocks and minerals that have these possible radioactive elements. The most common radioactive element to be exposed to is radon-222. And this is because it is an inert heavy gas. It tends to collect in basements. It comes from a rock source, and in Ohio, this is very common. I don't know how many of you may have a radon system on your house. I do. It was installed before I moved in because the amount of radon detected was higher than what's considered safe. The problem is that it is inert, so it doesn't react with anything, but the gas builds up on the floor level, and it tends to collect in basements because it's coming in from the rock around you in the ground. And so it breaks down and then settles in the basement area. So radon systems are designed to basically vacuum that gas up and eject it out of the house. And so that's what I've got on my house, is basically a vacuum that vacuums the gas off of the floor of my basement and ejects it out of the house constantly, to be able to keep that level low so that we're not exposed to this radioactive gas. So as far as dosage goes, you may have heard of some of these words, so we're going to talk a little bit about what they mean and what kind of exposure you get. So they're going to be measured in either rads or rem. Most of us have either heard of one of those two. So what does this mean? So rads, a rad is equal to, as you can see here, 0.01 joules. So remember, joules is that measurement for energy. So it's a 0.01 joules of radiant energy absorbed by a kilogram of tissue. So it's a very small fraction of energy absorbed by a decent amount of tissue. And the thing is that this is why we have two measurements. So the rad is the amount of energy absorbed, but not all radiation is equal. So remember, alpha radiation, beta radiation, gamma radiation all have different levels of damage depending on, what they're going to be doing. So this is why we have REMs. REM is calculated by multiplying the rads by a factor of damage for the ray or particle. So to give you an idea, 1 rad of alpha particles is equal to 10 REMs, while 10 rads of beta particles is equal to 10 REMs. So you can be exposed to more beta particles and accumulate the same amount of basically damage as if you were exposed to less of those beta particles. So this is why we have the REMs. That is actually going to take into account the damage that those particles are going to do with the energy exposure as well. So that just is so that you understand what those two terms mean. So RADS is talking about the actual energy absorbed, but REM takes into account the amount of damage that those are talking about. And so that's why we actually generally talk about these in REMs, because it takes into account both of those parts. So let's talk a little bit then about what kind of exposure we're talking about for us, because usually when we hear radiation, lots of people panic because we're like, oh my gosh, radiation, that sounds horrible. So the thing is that a lethal dose of radiation begins at 500 REMs. So what does that mean? What is that equal to? And at that dose, you have a 50% chance of survival. So if you're exposed to 500 REMs, full body, 500 REMs, you have a 50% chance of surviving. Radiation therapy, like you see up here in the corner, that is going to expose a small area, just a fraction of an area, to about 200 REMs each day. We're using this to do things like cancer treatment. So we're trying to basically scramble and fry those cells in order to reduce the cancer cells. So how does this exposure rate as far as our everyday exposure? Well, all the radiation that you'll receive from background and medical procedures is less than 1 REM. In fact, we have to use millirems to measure our exposure. We can't even really measure it accurately in REMs. So you each are going to receive about 360 millirems of radiation exposure per year from all sources. So from background, medical procedures, consumer appliances, all of that. So that gives you a little bit of an idea of your exposure compared to the risk. It's very minimal um, in comparison to an actual lethal dose. So here's the breakdown if you're curious about where that exposure is coming from. So a little of it's coming from cosmic radiation, some of it's coming from ground radiation. There is that air, the radon. I told you a lot of that exposure is coming from there. Just human tissue, yep, we have it too. And then here are the human origin ones. So you've got things like x-rays and any nuclear medicine. So not everybody's going to have this one. So again, this is just average. There's our TV and other consumer products. This TV tubes, this one's not as common anymore. This is the old style TVs. And then we all are exposed to about 1 milliram of radiation from the nuclear weapons testing fallout that happened when they were doing those weapon tests in the 40s and 50s. So yeah, we still have those left over as well. All right, so this is about you. I'm sorry, this topic is part of what your lab is about that you've got. So Half-Life is not just a video game. It also is talking about how long it takes for those radioactive atoms to decay. So a half-life of a radioactive element is the time it takes for half of the original elements, or I'm sorry, half of the original atoms to decay from being radioactive to a new form. So you can see up here we've got a little graph. So we start off with 1 kilogram of our radioactive element. And in this case, by the time we get to half a kilogram of the radioactive element, 1,620 years have passed. So that is a half-life. And then the next time around, to get from a half kilogram to a quarter kilogram, 3,240. So you can see we've doubled the time. And so this is what we're looking at as far as a half-life. So the element that you're seeing actually in that chart is radium-226. Now remember, when you see an element written like this is an isotope. So a lot of the radioactive elements actually have different isotopes, and every isotope has a different half-life. So the decay rate is different. And we're going to actually see too in the next lecture that there are radioactive forms of lower number elements. Most of the elements we focus on for radioactivity are those higher number elements, but we'll also see that there are lower number radioactive elements. And the radioactivity, the half-life changes drastically depending on the element. So there you've got radium-226 with a half-life of 1,620 years, and then you've got uranium-238, which has a half-life of 4.5 billion years. So the uranium has a half-life of about the age of the Earth. So all of the uranium-238 that was formed with the planet, about half of it has now broken down. So what's really interesting about half-life is that it is remarkably constant. It's not affected by external conditions. So it's not affected by temperature, moisture, anything that we can throw at it, the half-life stays constant. So it's been very helpful for us to be able to use for dating, as far as fossils and so forth, which we're going to look at in our next lecture.